we'll take the limit as theta goes to 0 of sine theta over theta. This is necessary before we can start talking about derivatives of trig functions. First thing we'll do is consider only what happens as theta is going to 0 from the right. So we'll consider the limit as theta goes to 0 from the right of sine theta over theta. We have to use the unit circle to figure this out. I have to do a little geometry. Because we're taking the limit as theta is going to 0 from the right, everything's going to be positive. So I'll look at just the first quadrant of the unit circle here. So we'll draw this right here. It'll be part of the unit circle. And we'll put angle theta right here. Now the angle theta looks kind of big in this drawing, but of course it's approaching 0, so it's really very, very small. And we can figure out this length right away. Because it's a radius of the unit circle, we know it's just 1. And I will drop an altitude right here, make a right angle. And we want to figure out what this length is. We'll call it h. I know that sine theta in the right triangle is opposite, which is h, over hypotenuse, which is 1. So that means that h is sine of theta. So I can write that down right here. This is sine of theta. I'm going to do the same thing right here, extend this out a little bit. I have another right angle here. Now, we can't use sine this time because we don't know what this length is. At least not right away. But we do know what this length is. That's also a radius of the unit circle, so it is also 1. So we know that tangent of theta in the right triangle is opposite over adjacent. So perhaps I'll call this to be h again. You know that tangent of theta is h over 1. So that means that h is tangent of theta. So I can put that down right here. And now we can set up an inequality. We're going to compare the red piece, sine of theta, with the arc. I should probably make a note. What is the measure of this arc right here? Because we know that this angle is theta, that means that arc has the same length. So we're comparing sine theta, and the blue length, which is tangent theta. We know that sine theta is the smallest. Let me put these down in black. Sine theta is the smallest, and tangent theta is the largest. And because theta is approaching to 0, we have to include the equal part. Now, I want to get this center piece here to be sine theta over theta, because that's what we're looking for. So to start, I'll take the reciprocal on both sides, on all parts of the inequality. When you're dealing with two positive numbers, for example, 2 is less than 3, when we take the reciprocal, we have to flip the inequality. 1/2 is greater than 1/3. And because we're dealing with just the first quadrant here, everything is positive. Sine theta, theta, and tangent theta are all positive lengths. So when we take the reciprocal on all the parts of this inequality, we have to flip the inequality. So the reciprocal of sine theta is cosecant theta, which is less than or equal to. The reciprocal of theta is just 1 over theta. 1 over theta, which is less than or equal to the reciprocal of tangent theta, which is cotangent theta. And now I want to get the sine theta on top here, so I'll multiply all the parts of this by sine theta. So firstly, sine times cosecant will cancel out, and we will just be left with 1. Cosecant is the reciprocal of sine. And because we're multiplying, sine theta is positive, we multiply by a positive number, we keep the inequalities the same direction. Is less than or equal to sine theta over theta, which is less than or equal to, we have cotangent times sine. Cotangent is cosine over sine. So the sines will cancel out, and we'll be left with cosine theta. Let me put that down once again in blue. And now I will take the limit as theta goes to 0 from the right of all the parts of this inequality as theta goes to 0 from the right, limit as theta goes to 0 from the right. All right, the limit of a constant is that constant. It's less than or equal to. This is what we're trying to figure out right here. Limit as theta goes to 0 from the right of sine theta over theta. All right, and then the limit as theta goes to 0 from the right of cosine theta is just cosine of 0, which is 1. And now I'll put that down in purple, why not? Blue. That tells us that by the squeeze theorem, because we know that this limit is between 1 and 1, we know that the limit as theta goes to 0 from the right of sine theta over theta is equal to 1. Are we done yet? No, we are not, because we have to consider the left-hand limit, the limit as theta goes to 0 from the left of sine theta over theta. To help us out, I'm going to look at this fraction right here and multiply top and bottom by -1. So this will be the limit as theta goes to 0 from the left of negative sine theta over negative theta. Sine is an odd function, which means I can take this negative in front and put it inside the sign. So this will be the limit as theta goes to 0 from the left of sine of negative theta over negative theta. And now I'm going to make a substitution. I'll pick t, perhaps, pick t to be negative theta. And I'll rewrite this limit in terms of t. So t is our new variable. So the first thing we have to do is figure out what does t go to. If theta is going from 0 to the left, from the left, because this negative right here, that means t will be going to 0 from the right. We have sine of negative theta, which is just t, over negative theta, which is also just t. And we already figured this limit out. This right here is equal to 1. So because the left-hand limits and the right-hand limits are the same, our conclusion is that the limit as theta goes to 0 from both directions of sine theta over theta is equal to 1.